What did you learn about the process? So, while you were working on this, what did you learn about the process of modeling data? What did you learn? What's one thing? Raise your hand. Let's use hands. Let's use hands. Hands. You didn't learn anything new about the process. Yes? Yep. So your results may be surprising? Oh, you need to be careful about understanding your predictions. What else? Yeah.
You need to really understand what the graph is exactly showing you. I know for mine, it says just energy per capita, but then like more finer print says specifically oil.
Oil, yeah. There's other types, yeah. That's a very good point. What else? What else did you learn in the process? Yes. Depending on the model. Yep. What else? Yeah.
You really need like a lot of points because if not,
What about the process of finding data? What can you tell me about that?
you need to be really specific about what you want.
You need to be very specific about the data you are looking for. What else? What else can you tell about the process of gathering data? Can you give me a simple statement about it? Yeah. It's hard to find good data. What else did you learn about the process? The easiest place to start, and I really got to start teaching you guys how to use the internet, but I'm failing, I guess. The easiest place to start is Wikipedia. Sure. Absolutely. The numeric accuracy of the data on Wikipedia challenges, if not beats out, every other print version of the statistics you see. It's a very bad idea to take stuff directly from, but if you follow the source links, where do you end up? Good sources. Yes. Best place to start, not the place you start and terminate your search. Something like 42% of Americans used Wikipedia last year. That's a lot of people. What else? What else did you learn? I want to expand on this. Be wary of any source. Any source. Did you learn anything else about the process? Okay, what did you learn about your data? Conclusions. What did you learn? What did you learn? Someone give me one thing. Yeah.
I actually did China instead of England.
That's fine.
Okay.
So this is energy, U.S. versus China.
Yeah.
Yeah.
China, like overall, they use about as much wheat as we do now. So per capita, we're a lot higher.
Yeah. What else? Other conclusions, other things, predictions, conclusions. What else? Yeah.
The amount of cars in the U.S. is like steadily going up.
Has been steadily increasing.
Yes.
Yep. What else?
There's no consistent amount. Over time the United States uses a lot more energy.
Okay, can anybody give me predictions or something specific about these things? More specific? Can anybody? Yeah, what did you... yeah? Yep. Yep. In the United States? By 2031, we predict there will be 1 vehicle per person on average. What about you, Pang? What do you got?
I did the global production of motor vehicles.
Yep.
And I got negative number for the year 2011. So I guess like the car is decreasing.
It could, yeah. Global production of motor vehicles, our model may not be too accurate too far into the future. What else? Yeah, Claire.
So my graph went up to 2000, but I only had 5 points, so I don't know how accurate it is.
Which data set did you work with?
I worked with the cars per household.
Cars per household, yep.
And so I had a perfect only sort of
Uh-huh.
5 cars per hour.
Got
So
it.
went up almost over an entire car.
It's going up quickly.
Yeah.
Anything else? Other conclusions? Yeah.
I found out that in this year, 2011,
Yep.
U.S. will be using 7,583 precipitate. The unit is kilograms of oil equivalent precipitate.
Per capita?
Uh,
Person?
Canada,
Yeah. Sure.
And the UK will be
Whoa. Yeah.
using 3,399.
Oh, that's depressing. Other conclusions? Anything else? Okay, that's pretty good. I like that. Here's average weather for St. Johnsbury, Vermont. This is average over the past, I think, 150 years. What I'd like you to do, find a model that fits this data. By yourself without talking, with your calculator. Find a model that fits this data set. Up with a graph that look like that. Something like that? Something like that. Can someone tell me one function they came up with rounding to 3 decimal places? What's your function rounding to 3 decimal places?
Y equals 27.433 sine 2475 x over 1.831 plus 41.432.
Okay. Who has a different one? Yeah.
0.039, x to the 4th.
0.039, yep. X to the 4th, yep.
Minus 1.109.
Yep.
X to the 3rd. Plus 9.0511 x to the 2nd. And then minus 15.817 plus.
Okay.
I got the same thing.
Plus what?
Plus 23.1.
Okay. Who has a different equation for me? Something different. Something different. Something different. Anybody else have a different model? Different model? You didn't try any others? Okay, so what's your prediction? Prediction. What does your model tell you the prediction for January of 2014? Who has a prediction for me? What's one number? What's one number, yeah?
16.9.
Which model did you use?
The second one, fourth reg.
For 2014, it came out to 16?
What?
Your quad reg came out with a prediction for January 2014 of 16. I need to see your data.
Yeah.
I'll take a look.
To get that one.
How do you get January of 2014? If this was 2010, right here, what would you have to plug in for 2014? What? 49. Right? You need to do 49. Is that what people got? Did people get 16? I didn't get that when I did that. Yeah, when I did this, I got the same thing. And when I do y1 of what? 49, right? That's what I said to do. You end up with? I got that right there. 55.55. Anybody come up with a different prediction? You use the quartic. Yeah, what'd you get? Okay, hey Brett, put the calculators down, everybody. Please tell me what your prediction was using your model. Yes. Yep. Thank you. Finally, someone's giving me an honest answer. Congratulations. Anybody else have a different answer? Yeah. 16. Using which model? Huh. Okay, that's strange because I have that model right here. 27.432 plus. Okay, so here's the deal. So I asked you the question, using this model, what does the model tell you the predicted temperature will be? What does the model tell you? So I did y of 49, and it came out to be... Okay, so are you guys getting 16 when you actually plug in 49 into your model? What? Okay, got it. Moving on. Point being, do you understand what I mean by using your model? Using your function, what does your function predict? And in this case, the function predicts 55. Now, what's the problem here? What's the problem? Well, that's one difference, but let's look at reality. That's the problem. Yeah, first of all, 113,000 degrees. No. And what about 55.5 F in January? What's the problem with that? Too warm. Way too warm. It's inverting poles, kind of temperature changing. So you need to keep an eye on reality. So in terms of temperature fluctuations, which model do you think we should go with? For temp models, which one do you think looks like it works better? Yeah, this one right here. What model is this? Yeah, these are trig models. And on your calculator, that's SINRAG, which is, what does that stand for? Sine regression. I think it's actually sinusoidal regression. It uses the sine function. So the reason this is helpful is because if you actually go back and graph this, and you change, so that's just from 1 to 12. If I change the window from that to, I don't know, 50 right here, what's this graph going to do? Up, down, up, down, up, down, right? Is that more natural in terms of every year the temperature is going to do something like that?
Yeah.
Doesn't mean it's going to be super, super accurate going into the future, but temperature oscillates. Temp oscillates. Moves up and down, repeats. Does that mean it's always the same every year? Not quite always the same. What's generally happening on the planet right now? Generally seeing a planetary warming. So that gets wider, but it also goes higher. I mean, it depends on where you're looking. Now, here's a big question for you. What can you tell me about climate modeling? What's one thing you can tell me about climate modeling? Be more specific, or
Take it all the factors into account.
well, you need to be more specific. I'll be more specific in my question. What general things have you heard about climate modeling? You've never heard about people talking about climate modeling, ever? You've watched, like, the news before, right?
The weatherman.
Politics. You've never heard a politician talk about climate change, ever?
Yes.
Okay, so what's one challenging thing about climate modeling? What makes it challenging? Yeah.
Is there like a time lapse when like the carbon goes there and then there's time?
I'm not specifically talking about carbon. I'm not specifically talking about one thing. I'm talking about, in general, when you're trying to model climate. You're trying to model climate. What? Climate changes all the time. Yep. Never holds still for you, right? What else? Yeah. It's very hard to predict. Now the question is why? Why is weather very hard to predict?
Because there are always some factors within.
There are always more factors to consider. The entire system of climate, when I say climate modeling, what are we talking about? What is climate?
The weather.
So what does that mean specifically? What is climate? The weather. Everything. Climate, by definition, is a huge field. What's another reason it's really challenging to model climate, to make climate models? What's another reason it's really hard? What's the basis for all climate models? Yeah.
Like it's moving back and forth.
Yeah, it's not static. That's true. What makes it easier to model something?
It's like science graph is tends to repeat.
I want to think more generally, everybody. What makes it easy to model something? Yes, when there's a trend. But please, in terms of questions we have looked at, when is it easier to model something and when is it not easier to model something? When you have more points. Exactly. Now, what can you tell me about climate data? Let's go back to this. Always more factors to consider, right? So what does that mean about the data you have at hand? If there's always more factors to consider, what does that mean about the data you have on hand?
It's not.
What? Why do you keep on saying that? Oh, man, why do you keep on going back to reliability? I know you have this obsession with it. I'm not talking about reliability. Okay, let's wait. It's gone. Okay, we're not talking about reliability. I'll ask the question again. Why is it hard to model climate?
Only in a specific location.
The what's bigger?
The world. One climate, one place, we need it for
Okay, we're gonna pause. Why is it really hard to model climate? What's bigger specifically? The information, meaning what? It's really hard to model climate. Why? Nope. Yep, because there is an overabundance of information. Too much information. Bucket small, ocean big. What's another reason? So, if I gave you data and it's bad, what about your conclusions, even if your methodology is really good? What happens to your conclusions? If your data is bad, your conclusion is bad. Okay, good. Thanks for keeping up there. Good. Okay, so in terms of climate data, since there's so much of it, what is there controversy over? There's many things that it's over, but what specifically with regard to the data, what could there be controversy over? So first, controversy over how to interpret it, and what else? Why would you take data out? What do you mean? What do you mean take it out?
Analyze all the data at one time.
Look at one specific part of it.
Yeah, but okay, let's say, is there one person in the world that measures the temperature at every point on the planet? Is there one person that just does Hawaii? Is there one person that just does Vermont? No. What are there? Multiple sources for what?
Data.
All data sets. So what does that mean in terms of analysis? If there's multiple sources, why? Why could there be multiple answers?
Not everybody does it the same way.
Ah, the data could be, if you measure something and you measure something and you measure something, are you guaranteed to have the same data?
No.
No, so the data could be different from different sources. So you have so much data, you have an overabundance of data from too many sources, and there's controversy over if it's valid or not, which sources are good, which aren't. Does this make modeling extremely hard to do?
Yeah.
It makes it very, very hard to do. Some of the most powerful computers on the planet, well, computers on the planet spend almost all doing what?
Trying to model it.
Modeling climate. Now, why is it important?
It influences our lives.
Be more specific.
Like if there's a tsunami, we need to know.
It would be nice to be able to do what?
Get out,
Predict
get away.
natural disaster.
Yeah, predict crisis events. It would be pretty neat if we could actually, with some regularity, predict major weather events.
That'd be nice.
Yeah. Why else? So besides predicting crisis events, why else would it be important to predict climate? So we know when we'll have snow days. Best answer yet. Okay. What else? What's the primary reason this is such a contentious topic? Can you be more specific? I want something more than a noun. Ah, climate models help potentially tell us about our future environment, which gives us a reason to change how we do things. Is that a rather contentious topic? Absolutely, absolutely. I have just a general question to poll for the class. The general scientific community all agree that what is happening? Yes, they agree that the climate change, you can be more specific.
Global
The global, okay, ready? We're not allowed to use nouns as answers anymore, okay? We need to use a sentence, okay? A verb is not a sentence, a noun is not a sentence. Okay, so use a full sentence here. The global scientific community generally agrees what?
The world as a whole is in a warming trend.
Yes, there we go. That's specific and general at the same time. Very good, I like that. Excellent. As opposed to, what's your favorite animal? Orange! Okay. Things like that. Okay. So we're in a general trend. Okay. It's wicked, wicked hard to do. There's so many variables that go into this. I mean, think about it this way. How good are we at predicting weather right now? We have some work to do. Yes, absolutely. We definitely do. Okay, we're going to... Found this great data set for you. This is for Burlington. It's at BTV. What is BTV? Anybody know? That's right. You know what BTV is. Here are average temperatures for each month going back to 1892. It's good stuff, huh? I gave you the link to this data right there and there. Both links go to the same place. First part of your homework is going to be to analyze temperature data from BTV, Burlington International Airport. Come to at least 3 conclusions. Make them as specific as you can. Yes, please use your calculator and or Excel and or the computer program of your choice. You must use some graphics to support your conclusions. You must use some graphics to support your conclusions. That's the first part of your homework. Okay? Yes? So I gave you this data set right here. Oops. Let's say I gave you something that looked better than that, hopefully. Shh. Yeah, there is a tool. I'll find it later. Yeah. So let's say I gave you a data set that looks like this. And let's just say that each of these is 1. So it's a rough sketch. I know. I got it. Let's say I asked you to, by hand, model this data set with a quadratic model. What should be my first step? If I'm going to model this as a quadratic, what should be my first step? Raise your hand and tell me. What's the first step? First step. If I'm going to model this data with a quadratic by hand, what's my first step? Yeah. We already have a lot of points. What's our first step? First step. Before that, what do I need to do? Before that, what's my first step? Yeah. Draw it. Thank you. We're going to... So step 1, draw a parabola of what? It's not the line of, it's the parabola of best fit. Now we have what we want to actually write the equation for. What should we do now? Our goal, everybody, our goal is to find an equation. So we now have our parabola of best fit. What should we do next? Sure, let's find a vertex. I like finding the vertex. And we're not really going to find it. What are we going to do? We're going to... Well, let's estimate it. So we think the vertex is what? 5... -2. Sure. What should we do next? We found the vertex. What's next? Ah, I love the zeros, x-intercepts. Those are my favorite. So let's estimate these. Drumming should stop. I'm going to say that's 2.50. And what's this one? Let's say that one is 6, 7, 8.25. So we have a vertex and 2 points. Is this a lot of information? Yeah. So we have a vertex and 2 points. Are we always going to be able to estimate this? No, but maybe we can. And are we sure that this is the vertex? No, but it could be a good estimate for it. How do we come up, how do we determine, how do we build an equation based on this information? What's one way we could do it? You have a vertex and two intercepts. What could you do? I'll give you the leading question of what form will the answer take? We're looking for an equation. What's one form the answer could be in? Yeah, what is standard form? To answer that question, we need a value for A, we need a value for, and we need a value for C. We need those three values. We have 3 points. Theoretically, we could substitute and get some answers. Are we guaranteed to have a parabola that goes through these 3 points? Yeah. Is this necessarily the vertex? No, but we're guaranteed to have those 3. What's another form it could be in? And this is an easier form to work with. There's another form of a quadratic. I know you've seen it before. Has something to do with that point right there? That's a formula for solving for the zeros, but we're not going to do that. It's going to be y equals, has anybody seen this before? A times x minus h squared plus k. This is the one that you really like if you have a vertex, because what is this called? Vertex form. Let's go with vertex form. What is the vertex in vertex form? HK. So in terms of what we know already, what do we know about this equation? It's going to be y equals what? A times 5 squared plus 2. We now have all the values except for what? A. How do we find A? Someone new who hasn't spoken. How do we find A? Minus 2. Thank you. Yes, minus 2. How do we go about finding A? Substitute. Either point. I like that one a little better. So let's plug it in there. So 0 is equal to A times 2.5 minus 5 squared minus 2. So that turns into 2 is equal to 2.5 squared times A. Negative, right? So what does A equal? 2 over 6.25. So what's the equation if we don't simplify any further? Y equals what?
2 over 5 squared minus 2.
Absolutely. Absolutely. Now, I like that because we assumed we had the vertex. We assumed we had the vertex. Let's say we weren't as sure. We weren't sure that was the vertex, but let's say we were 100% positive that these right here were definitely the y-intercepts, and we were pretty sure that was the vertex. To warm you up a little bit on this method, let's say I gave you this equation right here. Who can factor that for me? Who can factor that for me? Claire. Close. What are the zeros of that polynomial? If I set this equal to 0? Yeah, so x is equal to -2 and -3. So here's something I need you to look at, and we're going to talk about this at length. And I know you've looked at this before. If these are zeros, those are zeros of the polynomial, what are each of these called? X plus 2 and x plus 3. These are zeros. What are these? They're called, well, 3 and 4 are both factors of 12. Oh, I just said it out loud. They're factors. Wow, I don't know why I do that sometimes. Each of those are factors. So here's the deal. We factored, got factored form, and then we ended up with the zeros. So with x plus 2, what was the 0? -2. With x plus 3, what was the 0? -3. So let's say I gave you the zeros. If the 0 was 5, what's the factor? X take away 5. Exactly. So let's go back up to what we know up here. You see this? We have two. Let's say we were sure that those were the zeros. Or we're really sure those were the zeros. If these were zeros right here, if those are zeros, what are the corresponding factors? If 2.50 is a 0, what's the factor?
X minus 2.5.
And x. So we have this right here, but there's something missing, something out front. What could be out front? An a value. Now, give me 30 seconds here. How do you solve for that a value? Yeah, let's substitute in 2.5. So it was when x is, so this was 0, you have a 2.5. Well, you can't really use 2.5 in this case, can you? We can't plug in the zeros. We have to plug in the third point. What was the third point we had?
Vertex.
The vertex. It was what? 5, -2. I'll finish this up. -2 is equal to a times 2.5 times -3.25. So a is equal to 2 over 2.5 times 3.25. Is that actually pretty close to our other a value? Yeah. Your homework tonight, everybody, is to do the first part of that. Is to do that data set analysis, but you have a second part of your homework. Second part of your homework right here. It's pretty simple. It's going to be, you're going to do the data analysis, but you're also going to watch the video. I'm posting a video called Rational Functions on the U channel. Make sure you watch that video and come in with at least 2 questions about it.
Mr. Seamon?
Hold on.
I lost.
Hold on.